Hello everyone, my name is Manish Sahu and I'll be presenting a work simulation to real domain adaptation with teacher-student learning for endoscopic instrument segmentation. Endoscopic image segmentation is important for surgical scene understanding. However, deep learning-based solutions require a large amount of data with clean annotation. The annotation process, especially pixel-wise, can be relatively expensive because it takes valuable time of the clinical experts. A promising way to tackle this problem is to employ simulation-based learning, which not only provides data, but also clean labels for training of deep neural networks. However, the network trained purely on simulation data perform poorly when tested on real data due to the domain gap issue. This is mainly because the heterogeneity of the surgical scene is heavily influenced by the factors such as lighting condition, motion blur, blood, smoke, and specular reflection. However, the simulation data only mimic shape of instrument and patient-specific organs. In order to tackle this domain gap issue, our previous approach observed that the instrument shape remains consistent between the different domains and across semantic transformation, and therefore introduced a joint learning approach for end-to-end learning, where the deep neural network interplay between consistency learning for real data and supervised learning for simulation data. Here, the DNN learns to learn about instrument structure from the labels of the simulation, and it remains to be consistent against semantic transformation for unlabeled real data. And overall, joint learning enforces the model to be unchanged for arbitrary semantic changes and focus more on the structure between the real and simulation data. This approach showed that the generalization capability of network can be improved by employing joint learning approach and can improve the performance generalization capability. Let's see how the consistent learning part here provides supervisory signals and how we can improve on it. Here we just assign different name to the consistency learning part, the model, the teacher and student for easier understanding. So in this formulation of teacher-student, we can see that the teacher is the one who actually produce pseudo labels similar to supervised learning for supervision, and student is the network that learn from these pseudo labels. But this in current student as teacher scenario, the TNN acts as both a teacher and a student, so it can suffer from the confirmation bias problem because it's self-generating the pseudo labels, which may be incorrect and noisy during training, and it can reinforce itself to overfit to incorrect labels produced by itself and prevent learning any new information. In this work, we address this confirmation bias problem of the network by improving the teacher network, that is the pseudo label generation process of the unlabeled consistency learning part. So for this, we decouple the teacher network from the student and redefine it to produce stable labels as well as remain computationally efficient. So we choose it as a temporal ensemble of the student network. So we address this confirmation bias problem by redefining the whole architecture where the network learns by instrument labels from the simulation, and stable pseudo labels are provided by the ensemble teacher for the inconsistency learning part. So the overall joint learning enforces model to remain unchanged for local transformation and therefore focus more on semantic and structural changes between the real and simulation data. For our experimentation, we chose 3 datasets with varying degrees of domain gap with varying conditions like different instrument types and surgical scene and background changes due to different surgical procedures taken into consideration, and as also the counterexamples for what an instrument is and what is not is also these conditions actually together make the domain go apart from simulation. And it is important to note that the domain gap not only changes from simulation to endovis to collect robust myths, but also across 3 datasets from the robust myths, which are having different colorectal procedures at different stages. So here we have the table that shows quantitative results across endovis, collect, and 3 stages of testing for the robust myths dataset with increasing level of domain gap. Here, the blue and the red row shows the two baselines, that is pure simulation-based supervision and pure real supervision. And the substantial performance gap between these two baselines indicate the domain gap between the simulated and real data for the instrument segmentation task. Across the data set, we can see that this region for COLEC highlights the comparison of different unsupervised domain adaptation approaches. For instance, the style transfer approach I2I and the previous endosim to real approach. And we see that across the data set, our newly introduced approach outperforms the previous approach by a significant margin. However, we still see that there is a remaining performance gap with the real data, so it calls for identifying the remaining issues so that we can know how in future we can work and improve the results. So in order to do that, we investigate performance degrading factors to highlight the challenges in simulation to real domain adaptation. In this figure, you can see the Violin plot and within the three categories. This green is for the high peak of the Violin plot, orange is for the middle part, and red denotes the worst performing cases. Within the images, the green color represents the network predictions and the yellow represents the under-segmented regions. Our approach works best on the specific endovis data set, and it is less affected by the artifacts such as blood, smoke, or motion blur. However, the cases such as tool-tissue interaction and partially occluded instruments are the degrading factors, along with false detection on specular reflection and under-segmentation for these small instruments. For COLEC dataset, we performed an extensive analysis as instrument-specific labels are available for it in comparison to endovis dataset. In this figure, we see different instrument tool co-occurrences in the middle and the associated frequency associated with it, and below we see the dice performance across all these tool combinations, and we see that our approach generalizes across unseen instrument cases which are not present in the simulation. However, the counterexample cases such as specimen bag has poor performance, as specimen bag is considered as a non-conventional tool-shaped like instrument, but it has a reflective surfaces which in general produces false detection. So visual analysis on it shows that apart from the factors that was degrading endovis performance, other challenges factors include false detections on out of distribution cases like specimen bag, as we explained earlier, and the trocar view, which was in general missing in the simulation images, and other are the artifacts with which produces instrument shape-like appearance. On the robustness data set, we show additional performance degrading factors such as counterexamples for trocar view and non-rigid tubes, which produce again an instrument shape-like appearance. This also highlight weakness of our approach is that if an object produces an instrument shape-like appearance, it could be detected wrongly as instrument. And moreover, the addition of counterexample as bandages also lead to decreasing performance. Overall, if we plot the metric distribution across the dataset for all these three datasets we considered, we see that a majority of the performance drop comes from the endoscopic frames, where network produces false positives for the cases where it does not contain any instrument. And a direct relation of it can be seen actually in this table, where the dice score actually decreases as the number of empty frames increases from endovis to robustness dataset. This suggests that if we utilize false detection techniques in the current framework, it can enhance the performance generalization capability. So overall, for our work, we can say that we introduce a teacher-student based simulation to real domain adaptation approach, which is computationally efficient and enables end-to-end learning. Evaluation across three datasets shows consistent improvement in performance generalization capability, in the presence of unseen instruments and its combinations. Quantitative and qualitative analysis highlight the failure modes that are interpretable from simulation to real deep learning, and as the domain gap widens progressively. Finally, because our proposed approach is flexible, end-to-end, and unsupervised with respect to the target domain, it can in general be employed to, it can be further be extended and applied to other tasks, such as it can be combined with the style transfer approach, where simulation data and simulation data can be added with the real data style to produce a style data set, and then further be employed with our approach from where target data is select real and source is the style data set now. And if we do this thing, we see that in combination of our approach, if we employ it with the style transfer approach such as eye-to-eye, the performance jumps closer to what we can obtain from the direct real supervision. Overall, it can in general be extended to other imaging modalities or learning tasks. For instance, this same approach can be applied for the depth perception and pose estimation task by employing the depth and normal labels that are also available from the simulation. Finally, we can say that our work, which results in an extendable simulation to real domain adaptation approach, it's provide a direction which leads to annotation efficient surgical data science for the future WA. Thank you for your time, and if you have any questions, you can follow the paper, or if you have any specific questions, you can also contact me via email or the provided information. Thank you for your time.